Number one, I apologize if any of you thinks that I don't want you here because you only have 2 occasions. That is not how I meant that. If you only have 2 occasions, we can't do random effects of time, but you can do lots of other things. So if you have 2 occasion data, I'd be happy to chat with you individually about how to make the most of it. You just can't do random effects of time. Other question, what happens if some of your sample doesn't have longitudinal information? Some people only have 1 occasion, for instance. Do you have to throw them out? No. You can use whomever you have. The only question I would ask is why they only have 1 occasion. And if it is for a reason that you can identify, I would put that reason in the model as a covariate. If it's not for a reason you can identify, but you know who only has 1, I would at least put in a covariate for how many they have. That is the basis of what's called a pattern mixture model. That's work from Hedeker and Gibbons, and they talk about ways of basically conditioning your estimates based on how complete your data are. The easy way to do it is to put in covariates for how many occasions your people have. And then you could look at whether or not your sample estimates for the fixed effects differ as a function of subpopulation of how complete your data are. So in general, my answer is, like someone says, something went wrong with my data collection. Do I have to throw those cases away? No, but put it in the model. Put as much information in the model as to how those cases differ as you can, so that you can try to use all the data that you have, but yet still differentiate those cases in case it doesn't turn out that they're the same. All right, are we ready? Pick back up. And I was told they turned off the air conditioning, so it should be getting better. Apparently it was very, very warm in here yesterday, and they complained, and so they cranked it up and left it on. And so we're suffering the consequences. I'm not, actually. I get really warm teaching, so I planned ahead. But I'm sorry you guys are freezing. All right, where was I? I was here. We were about right here. Slide 25, we'll pick up here. So this idea then is partitioning variance. How much of what we're calling longitudinal variance is actually due to person differences, random intercept differences between people captured by this U0I term, and how much of it is actually longitudinal captured by this ETI term. And that lends itself to a nice descriptive statistic designed to tell us just that, which is intraclass correlation. So that term is used in a lot of different ways. There's a particular version of it here that's applicable to 2-level models. There's more than one version that's applicable to 3- and 4-level models, but it goes a little something like this. I have it written 3 different ways here. It's the proportion of variance that is between persons due to the random intercept over the total variance. So the total is both between persons random intercept and within persons residual variance. And so it looks like this. It's U0 variance over U0 plus E. And this will show up on your output in a couple of different places. I have an example here of that comes from SAS, where there's correlation versions of the matrices that we'll talk about, and you can ask for it as part of that. I'll show you software to do that in a second. The ICC has a couple of different interpretations. It's different ways of looking at the same answer. The easiest one is that the intraclass correlation is the proportion of variance that's between persons. That is, it's the proportion of variance that's cross-sectional due to mean differences, the proportion that would have been there had you sampled once. It's also the correlation of occasions from the same person. And that threw me for a while, thinking about why is the numerator between, but we're talking about the correlation of occasions within the same person. And you think about it in terms of prediction. If all of my occasions are very similar, I could easily predict one from the other. That's a very strong correlation. That would happen if there's not a lot of variation within my occasions, and it all has to be between instead. So a high intraclass correlation, like 0.8, that would be 80% between, 80% level 2, 80% random intercept, 80% inter, versus an intraclass correlation, say, of 0.3, then only 30% would be between. So we will do hypothesis tests to figure out whether or not this U0 intercept variance at level 2 is significant. ICC can be thought of as an effect size for that hypothesis test. It's a standardized way of expressing how much of our data is due to dependency specific to mean differences, so constant person dependency. So then we have a means by which we can put predictors in the model, and the predictors can be time things or people things or their interaction. And so the model for the means part proceeds a lot like regression. We'll do the same types of things that one would do in regression. The new part is paying attention to how the variance changes at each level. So after we put in between person predictors at level 2, we can talk about how much random variance in the intercept is left over, and we can compute an R-square for that. Likewise, after we put in within person predictors at level 1, we can think about how much of the level 1 residual variance is left over, and we can have an R-square for that. So after we get the piles going, then it turns into something much more similar to regression. So what I want to do is walk you through the transition from a general linear model to a model with the random intercept, just to show you what happens when you fit the right model. So here is a fake data example. This is from my book, Chapter 3. So yes, as I started teaching this material at the University of Nebraska, I became increasingly dissatisfied with the books that were out there for various reasons. And so rather than continuing to complain about it, I wrote one. It took 5 years. So I really hope that it's useful, because I wrote it for people who are trying to teach themselves and for my type of student. So this is an example from Chapter 3 then. 50 kids, made up data so that it's all very well behaved. Either in a control or treatment group, they were each measured twice. And the hypothesis is that the kids in the treatment group should change more between pretest and post-test. And so I have on here what we would call the cell means in ANOVA language for each combination of our 2x2 design, as well as the marginal means. And the terms in the boxes then are going to show up as model parameters. So let us take a look here. This is example 1. This should be in your packet. You'll have to go all the way through the end of the PowerPoints, and then you'll get to something that looks like this. Or it's a separate PDF file if you're playing along electronically. I put together these types of handouts so that nobody needs access to software. I found workshops where you're trying to run things along with the instructor to be not as useful. So I try to do all that before. But if you want to see what output would look like in a different program, for instance, if you want to sit and run this stuff in R with me, in the download packet, there are data sets within SAS, SPSS, and Stata, as well as example code and text versions of the output. For instance, this is what it looks like in SAS when you combine the log and the output, and so that way you can annotate these outputs directly if you want to, or run along in your program of choice. So we're reading in the data. I'm creating 2 new predictor variables. So in the original data set, time was coded 1, 2, and so was group. We will always be centering predictor variables so that 0 means something. That way we have a meaningful intercept. Always, 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 always. So I am creating a variable called time1, meaning that it's time minus 1. So the reference group then is 0 at pretest, and this is the effect of moving to the first occasion. That's how I think of it. So treatment then is the effect of being in the treated group relative to control. So the reference person in this analysis is a pretest occasion for the control. And so the same code would look very similar in the other programs. This shouldn't be anything that you haven't done before. And here are the cell means, the marginal means, and that's how I made that table, just to show you what the data look like. And so here's our first model. This is designed to introduce you to what mixed type of software for multi-level models looks like using models that you already know. So this is the first model that I talked about, the empty model that only has between-person variation in it. So this is dumping all of the occasions into one pile of variance. So we're not differentiating what is between versus within. We're just saying everything is E. So I know this is wrong, but it provides a point of comparison. So let's see. More people were SAS than SPSS, or SPSS than SAS. Is that right? Do you guys care which one we talk about here? Well, I can tell you how these things correspond. We're going to be using what is called residual maximum likelihood. I'll talk a little bit more about that, I think, later today. That is the same thing as least squares if you have complete data. It becomes something different than least squares if you don't. But REML is the preferred estimator in small samples. It matters less in larger samples where the sample size is based on the highest level. So when you don't have that many people, you should be using REML as your estimator, and that is the default, I think, in SAS and SPSS. Model outcome on SAS is how you tell it what DV you have, what dependent variable, the same thing as mixed outcome. By is analogous to class, so this is how you denote nesting variables as well as categorical predictors. I have seen models either not run or take too long when I don't include these variables here, and I'm not sure if it's superstition or if it's actually the case, but I always do that. So person ID is my level 2 identifier. It says which person is which. And time is my level 1 identifier as to whether it's pre-test or post-test. So right now, on the fixed line here, you can see there's nothing. Analogously, there's nothing before the option denoter, the slash here. This is an empty model, so no predictors. Yes, sir?
I have a question about REML versus ML.
Mm-hmm.
So I've heard before, like when you don't have a lot of people, REML's preferred.
Yep.
But how do you kind of quantify?
When's a lot?
Yeah.
30 to 50 is the general rule that I had heard, but it actually depends on how complex your model is. In practice, I would say stick with REML if at all possible. If you find that ML gives you the same inferences, then it probably doesn't matter. But the problem is that once you switch into multivariate, multi-level software or SEM software, there is no such thing as REML. So then you're stuck with ML. Some people would say Bayes fixes everything in that case. I am not one of those people. But that would be an alternative to ML, is to use Bayes with informative priors to try and help diminish some of that small sample bias. I made a picture, and I'm forgetting where it was. I'm going to go with chapter 5, maybe, where it has an asymptote. And I actually found that the estimates were not very similar until you hit about 100 people in making that picture. There is a formula that's in the book that uses n, level 2 sample size, and the number of fixed effects to try and figure out what the percentage bias is between ML and REML, and so you could probably plug your numbers into that to get a rough sense of whether it matters. Okay. Other questions on that? All right. So the repeated line here is used to identify the fact that we have 2 occasions within the same person. However, this cove type VC, this cove type ID, and this word independent here all say the same thing. We are fitting a regression model. We are fitting a model where all of the E's have constant variance across persons and time with no covariance whatsoever. So this is an independent model. We know this is wrong, but it provides a comparison. So here is what SAS output looks like. SPSS output will look very similar. We get something called an R matrix. This describes the variance and covariance across time. So since we only have 2 occasions, the first entry here would be the variance at pretest across persons. The second is the variance across post-test, and they are the same number because that's what we told the model to do. We told it to make it the same number. And the fact that I got a giant blank here where my covariance should be is that I didn't allow one. I told it not to put one in. I am saying there is no covariance or no correlation between occasions of the same person. This would be analogous to regular regression or a between groups ANOVA. So all of the residual variance is in one pile. The variance is 40. These things we will talk more about later this afternoon. These are indices of model fit. We don't need those yet. and here's my fixed intercept. So if I know nothing else about a person, and right now I don't, my best guess for their outcome on this test is 53. A couple notes on differences across programs in terms of the output that you get for your reference. Now let's fix it. Second model adds the partitioning of the variance into between versus within. So we're still not adding any predictors. We only want to know, before adding any informative information, how much of my variance is between persons level 2 versus within persons level 1. So I'm adding my U0 term to denote that we've added this level 2 variance term. And there are a couple different ways to do this in software. The way that translates most directly into repeated measures ANOVA is this type equals CS, CS, or exchangeable. That stands for, anyone want to guess? It's on your paper. You'd like to read it aloud and seem smart. I often do that to encourage participation. What does CS stand for? Compound symmetry. Yeah, you got it. That's a very statty word. That means equal variance, equal covariance. It means it doesn't matter whether it's time 1 or time 100. You get the same variance across persons. Likewise, it doesn't matter if you're talking about the relationship between time 1 and 2 or time 1 and 100. That's the same also. So equal variance across time, equal covariance across time. That's what this model is. So we're saying the only reason that occasions from the same person are correlated is because some people are higher on average than others. The end. This idea that some people are higher than others on average is quantified by this random intercept variance, which shows up in the off diagonal here to give us covariance. So it is the only source of covariance. The idea that there are person mean differences is the only kind of dependency. It's the only thing we need to worry about, and now we're good. That's what this says. So we still have the same total variance, which is 40, but now we're saying that 12 of that is because of this random intercept variance. So the diagonal that gives us the total variance at time 1 and at time 2 is the sum of the within, the E variance, and the between random intercept, the level 2. So the two numbers that gave us the sum of 40 then are reported here. The 12, that's my between person, level 2, random intercept, inter, and 28 is within person, level 1, E residual, intra. And this R correlation matrix here translates this covariance and these variances into a correlation matrix, and so it gives us the ICC directly as 0.3. So here's the formula by which you can do this yourself. Random intercept variance divided by random intercept plus residual. And this, by the way, this R-core is one of the main reasons I don't teach in SPSS, even though a lot of people use that, because it doesn't provide it. There's pieces of output that are helpful for pedagogy that are not provided by all programs. SAS has them, and so that's one of the reasons why I favor using SAS for this. So 0.3 then, that's a proportion. That's the proportion that is level 1 or level 2, folks? Take a vote. Level 1? Level 2. Level 2s have it. Most people abstain. That's okay. We're just getting started. So yes, 30% of this information would have been there had we sampled these people once. 70% is new information. 30% is level 2 mean differences cross-sectional between person variation. 70% is level 1 residual within person longitudinal information. Is that 30% different than 0? That's what this piece of output here is telling us. We'll talk more about this later, but it's doing what is known in statistics as a likelihood ratio test. This thing is also known as a chi-square test in SEM terminology, or a deviance test in, say, logistic regression, where we're looking at the change in this number relative to the previous model. So we'll go over this in more detail, but yes, this number tells us that 0.3 is not 0, as you might expect. But note, we still get 53 as our fixed intercept. That's because we fit the same model for the means that only has a fixed intercept. In practice, you will get different answers for what your fixed intercept is in a single level E-only model than what your fixed intercept is in a two-level empty model if your data are unbalanced. If each person has the same number of observations, then it doesn't matter if you first compute a person mean and then compute a sample mean of the person means, versus if you just find the sample mean of the whole data. The mean of the means is the same thing as the means if everybody contributes the same number of observations. But if everybody contributes a different number of observations, you get a different answer if you take the mean versus the mean of the means. This latter number here in the two-level model is the mean of the means, the sample mean of the person means. And the same thing will happen when we have fixed versus random slopes for predictors. It's either the mean slope or the mean of the means, the mean of the slopes. But these are perfectly balanced data, so the number is exactly the same. So let's add some predictors. Also giving us a chance to review how to do linear models in terms of main effects and interaction terms. Yes, ma'am. You don't have to do anything differently. You just have to know why the number changed and what it means. If you're concerned that the people who have fewer occasions are somehow different than other reasons, you could put in a covariate for how many occasions they have and use that as an interaction term for all your other things to see if they're different. People who have fewer occasions can't contribute to slopes that use later occasions. So if you have somebody who only has one, they can contribute to the estimate of the intercept. They can't contribute to any estimates of change. So you don't necessarily have to do anything different other than think about what is the implication of them having less data. Are they somehow different than the people with more data? And that becomes more of a selection bias kind of issue than a stats one. Does that help? Okay. Other questions while we're here? All right. So let's throw in some predictors and talk about how to get simple effects out of interaction models, because this is something I find people vary very widely in how well they've been trained to do this, if at all. Is anyone still being told that if you have an interaction term, you don't look at your main effects? Has that died yet? No, because it needs to. The only way to interpret an interaction is to look at your main effects. The question is whether they're simple main effects or marginal. Marginal main effects are what you get by default out of ANOVA software, and they are useless. Simple main effects are what allow you to say what the heck your interaction term is doing in the first place. So I do want to go over this because we're going to need these tools anytime we add predictors, because you will find that everything is going to become an interaction term in these models. So this is going back to our E-only model to contrast what happens to the effects of our predictors when you fit the wrong model for the variance, single level, ignoring the 30% of the information that's between persons, versus the right model. And I know it's the right model because I made up the data. Normally we don't have that luxury, but today we do. So I'm throwing in on the model line here in SAS, or on the fixed line in SPSS, or after the outcome on stata, C dot meaning continuous, with meaning a continuous predictor in SPSS, or the default in SAS. These are fixed effects. So I'm asking for the main effect of time, the main effect of treatment, and their interaction. And note this nice thing right here. You can define interaction terms on the fly with an asterisk. You don't have to make up a new variable. Certain programs make you make up new variables. You don't have to do that in any of these, which is very nice. In Stata, it's either a pound sign if you are over 40 or a hashtag if you are under 40. Take your pick. And stars and some of the other programs. The rest of this then is asking the model for the missing pieces of information. So we'll come back to that once we see what we actually get out of this. Yes, sir? They are different. That's a very good question. I forgot to mention that. So we have two different time variables here. We have original flavor time and new centered time. They do different things, and you do need both. Centered time is being treated as a fixed effect, and it is being treated as a continuous variable. For binary predictors, it doesn't really matter, but it will matter once we have more than two. It will go on the model line and also on what's going to be the random lines. So that shows up here also after the with statement in SPSS to denote that it is a continuous predictor, The with statement is the covariance box in the Windows version of SPSS, whereas the fixed factors box goes with by.
So time 1 is a continuous.
Time 1 is continuous.
And the time is
Original time is categorical. It is being used as an ID variable. It is not being used as a predictor. So original time goes on class and repeated in SAS, or on by and repeated in SPSS, or it is used inside this set of parentheses in Stata to denote the structure of the R matrix. So if you wanted to fit residual covariances between occasions, this is how you tell it which occasion is which. In a structure like we have here, where the residuals are uncorrelated with constant variance, it doesn't really matter, but it does matter if you have missing data and you want another structure. So without time on repeated here, let's say that you have time 1, 2, 3, time 1, 2, 3, and then the third person is time 1, 3. Without this time variable, the program will read that and go, okay, first observation goes in the time 1 column, second observation goes in the time 2 column, even if the second observation is time 3. So when you put the ID variable here, it knows which is which. That way not everybody has to have the same rows, and you don't have to insert missing rows as placeholders. So original flavor time is an ID variable. It is treated as categorical. Time 1 is a predictor variable that is treated as continuous. I'm sorry? Time 1 is centered so that it is 0, 1 instead of 1, 2, so that my intercept means something. Treatment is centered so that 0 is control and 1 is treatment.
Can we delete the class statement for the person ID here?
There's something about the use of class for denoting level 2 subject variables that if you don't do that, it either, I've seen it not run at all or take forever, and I think it has something to do with the pre-sorting of the data that it does if you invoke it on class. So I'm not sure if this is superstitious behavior on my part, but I just always do it. But person ID is also not a predictor. It is an ID variable to denote how the repeated observations are organized. Okay, yes?
Just a very quick question on the time variable. So if it's a balanced design, it doesn't matter whether you put time 1 or time on the class line.
It does matter because SAS and SPSS will yell at you. Because if you put time on the repeated line, it wants it on the class line. If you put it on the class line, it thinks it's a categorical predictor. You have to have two, and they have to be named different things. One can literally be a copy of the other, but they do different things in the specification of the syntax. Nope. Minus the mean is a common thing to do if your scale of your predictor is not meaningful and you just want to put it in the middle. More generally, all you have to do is have 0 means something. So when it comes... Yep, 0, 1 is a dummy, so is treatment is a 0, 1 variable. 0 just got to mean something. That's all. So we're not predicting the occasion before we started the study. which is not wrong, but very weird. Yeah, they do. Yeah, that isn't really a thing anymore. Modern software can handle that sort of collinearity. It changes the interpretation where you put the 0, and so we'll talk about that this afternoon in the context of models for change. Where time 0 is going to dictate what your intercept means and what your lower order terms mean in polynomial models. Others. All right, so let's see what we get then. So we have 50 subjects, 2 observations each. I'm on top of page 6 in example 1. So the variance went down from 40 to 27. So we've explained some kind of variance by adding time group and their interaction in. But this model doesn't differentiate what is between and within. It's all in one pile. This is a regression model, or a between groups ANOVA, as you might call it. And here are my fixed effects then in red, because this is my model for the means. And I have labeled what each one is. By the way, this is not SAS. This is what my students call Proc Lesa, helping you. So there's the interpretation of each one relative to the equation that we wrote. But if we look back at our cell means here, 49 in red, that's my reference point for the model. That's my intercept. The fixed intercept for your model is like the "you are here" sign. When you stare at a map in a mall or an airport, you got to know where you are first to know where you're going. So "you are here" is pretest for the control group. That's 49. Given the interaction term between time and treatment, each of these so-called main effects becomes a simple effect. It is the effect of the predictor specifically when the interacting predictor is 0. And that is why 0 has to mean something in each predictor for this model to make any sense. So time 1, that is the difference between pretest and post-test, specifically when my treatment variable is 0, which is the control group. So 5.8 is how the control group changed. That is significant according to conventional standards. Treatment, then, is the simple main effect of treatment, specifically when time 1 is 0, which is when we're talking about pretest, the first occasion. So the groups were different by 1.68 at pretest, which is not significant, which is good news if we believe in random assignment. And then we have our interaction term. And this is where sometimes folks don't get trained on what to do with this number. But interaction terms are actually quite straightforward. There are only 4 kinds in the entire world. You just have to figure out which of the 4 you're looking at. An interaction term takes its simple main effects and it makes them either more positive, less positive, more negative, or less negative. That's it. So if I look at this pattern, the main effect of time, let's start there, is positive. So in the control group, the difference between pretest and posttest is 5.8. In the treatment group, that difference of 5.8 becomes more positive by 2. So the treatment group grew more than control by 2. However, not even close. I can't even call this approaching significance, right? That's my favorite one of all the euphemisms. Trending, approaching. I like approaching because it makes it sound like if you just leave it alone and come back, it'll be there like a cake. You know, it's not quite done yet. But no, I can't even call it that. But even though it's not significant, we can still interpret the fixed effects for practice. So I could say either that the change becomes more positive by 2 in the treatment group relative to control, or to go the other way, I could start with the main effect of treatment and say the group difference is more positive by 2 at post-test. So of the possible fixed effects, we get 49 as my intercept. We get this simple main effect between pretest and posttest for control. We get this simple main effect between control and treatment at pretest, and we get the interaction. Now, if I want to compute what the other differences are, I can do that, because 1.6 plus 2 is 3.7. Likewise, 5.8 plus 2 is 7.8. But what I don't know is whether those new computed terms are significant. I need their standard error to be able to tell that, and I could compute that, but I'm lazy, so I'm going to make SAS do it for me. And that, my friends, is the world of estimate statements, which I drill my students to no end with because I think it's so useful and because I didn't know this until way too late in my life. I was taught that if you want the missing simple effects for an interaction, you need to recenter your predictors and rerun the model. Anybody being taught that? Yeah? Yep. Yeah, that's my crowd in the back, the people who say pound sign, right? Own it. Don't be afraid. That's right. I bet you match your socks, too, don't you? Because that is a thing right now, mismatching socks. I don't understand. But that's a whole separate conversation. So yes, I was taught to recenter and rerun the model, but that's annoying. I want to get everything I want to know out of one model, so I'm willing to ask for it. So I have a demonstration here on how to ask for any predicted intercept and any predicted slope. Some of these are the ones that we already have, and some of these are the ones that we don't have. So in these sorts of statements, you list what you want, and then you tell it what to do with the betas to get you that answer. So I have here the logic behind what these statements are doing. If I want to know what the predicted outcome is, I have to fill in both the betas and the values for the predictor variables to be able to get that. So that's what these first 4 lines are doing. All predicted means, cell means here in this case, get an intercept. They get the main effective time if they're for the group that time is 1. They get the main effective treatment if they're for the group that treatment is 1. And then I do the multiplication to figure out if the interaction term should be 0 or 1. And it only shows up as 1 when I have 2 1s as the main effects. That part's not so hard. That part most people have had experience doing. This part can be a little more tricky. To figure out what the model says the time slope should be for any level of an interacting predictor, you pull out the terms that have to do with time and time only. So if I take time and I factor it out of the main effect and the interaction here, I get a reduced little equation that looks like this. The main effective time starts off with beta 1, but it will only stay as just beta 1 if group is 0. So that corresponds to this statement right here. To get the time effect for the control group, I just need 1 beta 1, but I don't need any interaction terms. So these words actually refer to the fixed effects, the betas. I didn't need to write that because the model already gave that to me. To get the one that I'm missing, though, what is the time effect for the treatment group? I need a beta 1 plus 1 beta 3. And so I fill in 1 for the interaction term. So the linear combination of beta 1 plus beta 3 gives me the time effect for the treatment group, and it's going to give me the standard error and the p-value for it. Likewise, if I want to know the group difference at any occasion, I pull out of the model the terms that have group in them and only those terms, factor out group, and the main effective group is at a minimum beta 2 when time is 0, and it's beta 2 plus beta 3 times whatever value of time you're interested in. So then down here, this is the main effective treatment at time 0. This is the main effective treatment at time 1. So we're asking SAS to do linear combinations of fixed effects to get simple main effects in this case, but it's also useful to get differences in effects. And so there's lots and lots of uses for this. So that's where I got the rest of this output here that helped to build this table. So now I have my predicted means for any time for any group, as well as my time effects. So here's my time effect for the control group that the model gave me directly is beta 1. Here's beta 1 plus the interaction term beta 3, which gives me the 7. Here's beta 2, and here's beta 2 plus beta 3. So now I have the whole story. There is not a group effect at pretest, but there is a group effect at posttest. However, 1 and 3 are not different because this interaction term of 2 that tests their difference is not significant. Likewise, the control group grew by 5, the treatment group grew by 7, but 5 and 7 are not different according to this interaction term of 2. And thus, my summary, wah, wah. Okay, so questions on any of that beta stuff? All right, now let's see what happens when we fit the right model. We already know that these data are longitudinal and that 30% of the variation before we start talking predictors had to do with between person level 2 random intercept mean differences. So let's throw U0 back in and see what happens to my fixed effects. So we're switching back from a independence model back to what's called compound symmetry, or what I would call random intercept only. And so the code is exactly the same, save for the switch for the type of a repeated structure here. Now we have 2 piles of variance left over. So those are listed right here. 22 is the variance left over at level 2 between persons in the intercept. 4 is the variance left over in the residual within persons over time. The intraclass correlation for this conditional model, so after controlling for my predictors, how much of my remaining variance is between persons, that's actually much higher. It was 0.3, it's now 0.84. So this is a lesson to folks who ask, do I really need a multi-level model? Yes, and not just to keep myself in business. Even if the random intercept variance were 0 to start with, what's going to happen is that the estimation of the random intercept and the residual variances are yoked together. I'll show you that this afternoon, such that whenever you reduce level 1 residual variance, level 2 random variance goes up. So it is possible that you can have an intraclass correlation of 0 that becomes something large after you factor in your predictors. And in this case, it looks like, relatively speaking, the within model did a better job than the between model, because most of what's left is between. So the conditional intraclass correlation here is not something that I typically report, because it means 2 different things. It's a function of not only how much variance was level 2 between mean differences to start with, but also how good your model was at predicting each kind of variance. It commingles them. But this case, it does show why we're going to get different inferences, different p-values, different standard errors for some of our effects after we factor in this intercept difference. That's 84% of the variance that's left. So I have a, here's the within subjects solution. And I have it next to the between subjects, so we can do a side-by-side comparison. Let me move this out of the way for just a second so I can put them on the same screen to talk about. So this will be another easy audience participation game. Let's go one by one by the fixed effects. Fixed effect from the within person model on top versus fixed effect from the between person E-only model on the bottom. Same or different? Same. How about the simple main effect of time? Same. Simple main effect of group? Same. Interaction term? Same. They're all the same because it's the same model for the means. It's the same fixed effects. It's the same cell means. The difference is going to come in our inferences as to whether or not they're significant, which comes from the standard errors. So there's a pattern here. Intercept and treatment. Standard errors. Same or different? Same. So subject things, person-level things, are tested the same in both models. An intercept is a subject thing in this case because each subject gets their own. It gets the random intercept. Let's look at the time-related effects, the main effect, and the interaction term. Are their standard errors same or different? Different. Much smaller in the within-person model. That's because the within-person model thinks about error differently. In the between-person model, when E is the only variance component, all of it's error. All of it is sloppiness, as we talk about in modeling language. Like error is bad, right? It means you messed up your experiment. Error is variance in other places, but error is bad. But the within-person model understands that it's not fair to think about all the error as one thing, because time can't possibly explain why some people differ from each other. They were the same people the whole time. So it's not fair to think about error that's between persons as relevant to testing the time effect or its interaction. So this model, the within-person model on top, kicked out 84% of what we called error out of its test. And it tests it only against the 16% that's actually within persons, which is relevant. So more generally, in a two-level model like this, level 1 fixed effects like time, and in this case treatment by time, are going to be tested against level 1 error. Level 2 fixed effects, between person things, are tested against both, between and within. And look what happens to our lovely interaction term. Dun, 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 dun. So it's not magic, and it won't always make your results the way you want them. But in this case, fitting the right model meant getting rid of some of the error that was irrelevant for testing that interaction term, which is between person differences. And this is a roundabout way of demonstrating the difference between groups ANOVA and repeated measures ANOVA. The way that I was taught that is by thinking about that there's this constant person-subject differences that get kicked out of the denominator, and that's why repeated measures ANOVA is better for repeated measures designs. That thing that got kicked out of the denominator, it didn't get kicked out of the model. It's right here. It's random intercept variance. So what I've just shown you is the univariate approach to repeated measures ANOVA. It says that we can get rid of person mean differences when testing repeated measures factors, like time, and in this case, treatment by time is also a repeated measures effect. And for two occasion data, this is perfectly fine. The only thing that you could potentially add to this model would be to let the residual variance that remains differ between pretest and post-test. That'd be the only other thing that I might be tempted to do for two occasion data, but otherwise, you can only have a random intercept. Okay, how are we doing? Okay, so continuing along the ANOVA analogy then, here's my model. What if I thought about this model, instead of a two-way time by group design, as a three-way design, where I throw in person as another factor? I could do that. I have a 50 by 2 by 2. 50 subjects, by 2 groups by 2 times. Not fully crossed, but you can think of it that way. So if I have a 3-way design, then I could potentially have up to a 3-way interaction. So let's think of it from that perspective and see what effects are here and what effects are not. So within a 3-way interaction, I have 3 main effects, right? So do I have a main effect of time in my model? Yes. Do I have a main effect of group? Yes. Do I have a main effect of person? Tricky one. It's right here. That's what my random intercept is like. It's a random main effect of person. But in the same way that a main effect of time allows mean differences across occasions, a random intercept for persons allows mean differences across persons. The difference is that I'm estimating a variance across persons rather than every specific mean difference across persons that would come with it. So person is a random effect, not a fixed effect. I don't care about person 1 versus person 2 versus person 3. I care on the whole how much they vary from each other as a random sample. So U0 is the idea of a main effective person. So I do have 3 main effects. I also have the potential for 3 interaction terms. Here's one, time by group. That's a fixed effect. In this design, can I have person by group? If each person is only in one group, I can't have person by group. I don't have the information with which to see how somebody would have done different in the other group because they were never in the other group. So I can't estimate that. So because I can't have person by group, I can't have person by time by group. So there's only one left, person by time. Do I have that or not? I do. We're nodding. Where is it? That's E. Not only is it in the E, it is the E. E is person by time. E is person by time. So let me show you a picture here that goes with this idea. This is slide 31. Let's say that my orange person and my purple person are from the same group. So each group gets a different slope for change over time between these 2 points. So they're from the same group, they get the same slope, and they get the same intercept. U0 for the purple is the difference between the purple person's mean and the grand mean. Likewise, orange gets their own U0 also. Because the model says both of these people change the same, this U0 distance is time irrelevant. You can think of it as the mean difference between people, even though it's technically at the first occasion, because this model says the variance stays the same across time too. E then is the difference between the purple person's actual occasion 2 here and the one that's predicted for them, and likewise here, and likewise here, and likewise here. Or I could say, no, I don't need error. I got person by time instead. I'm going to let each person have their own slope. Now U0, I have to think about at a particular point because what U0 would be depends on where time 0 is. So we'll have an individual varying slope later on that is U1, that would denote this, but how well does a line fit 2 points? Perfectly. So it's 6 of one, half dozen of the other. Either you believe that there's error around the lines, or you believe that each person gets their own line perfectly. Person by time is the error term, and we don't have enough information to separate out what is actually person by time from residual. In order to do that, we need a third occasion. Then we can separate out what is person by time from what is error. And person by time is going to be the idea that we get a random time slope in addition to the random intercept. In the same way that we will talk about how U0 is how far off their intercept is, we will talk about what's going to become U1 as how far off their slope is from the main slope. So I want to make sure that you understand this so that you don't fall prey to some of the shenanigans that show up in the methodological literature. You ever heard of like latent difference score models, latent change score models? That somehow if you have 2 occasion data that SEM can save you? Nope. What happens in a latent change score model for 2 occasions is the right picture. In order to estimate that latent change, they have to pretend that there's no residual error. The model's not identified otherwise. So whether you think of it as error or perfect slopes, it's up to you. I find perfect slopes a little untenable, so I go with error. But there's nothing that can save you for 2 occasions. 2 occasions cannot differentiate these 2 situations. You need at least 3. And 3 is really the bare minimum. 3 is not good, unless you really do have linear change in a really strong signal. So yes, we do have a main effective person. We can't have a person by time interaction without sacrificing error. Not identified. Okay, how are we doing? So if I were looking at these results here, I'd be like, well, if this was my dissertation, and I got to pick whether this interaction term that's significant is right or this one, I'm picking this one. Now, wouldn't it be nice to have like an empirical way to say that? So reviewer 3 doesn't argue that you picked the wrong one. It's always reviewer 3. Well, there is. So it requires a different way of thinking about significance tests. So whenever we're interested in talking about whether or not we have a better model for the variance than an alternative, we have to do something called a likelihood ratio test. So I have a slide here that condenses all of this. We'll get more practice with it this afternoon. But on your output is a number that is called -2 log likelihood. That thing is an indication of misfit. Smaller is better. Where it comes from is in these models, they use the multivariate normal distribution to calculate the height of someone's data given the model parameters. They go through and find different parameters, try them out, see how tall each person's data is, take the log of that height, add it up, that's log likelihood for the sample. It tries out different numbers for the variances that then create the fixed effects until it comes up with the combination that makes the whole sample as tall as possible. That number is log likelihood. Log likelihood is scaled such that better is higher. Log likelihood is tallness, height. The difference between log likelihoods when multiplied by 2 is distributed roughly as a chi-square. And to get the chi-square to be positive, it has to be -2. So the software, such as Stata, SAS and SPSS, do you a solid and take your log likelihood and multiply it by -2 so that you can take the straight difference between models and make something of that number. In M+, and in Stata, they give you log likelihood instead. That is true for either ML or REML, which we'll talk about later. But what you do is take the difference. So it is always the model with fewer parameters minus the model that has more to create a positive result. So minus 2 log likelihood from the model with only one pile of variance in this case, minus the minus 2 log likelihood for the model with more. You then calculate the difference in the number of parameters that you had to spend to get that level of fit, which is known as degrees of freedom. The number of parameters from the model with more versus fewer. And you compare that difference in minus 2 log likelihood to a chi-square with degrees of freedom equal to that difference in number of parameters. So if you've memorized part of the chi-square table, like I unfortunately have, 1 degree of freedom for p less than 0.05 is 3.84 critical value, 2 is 5.99, 3 is 7.82, and 4 is 9.49. Those are the ones I use most often. So in this case of going, what? I'm not necessarily proud of that. I just happen to know it. I'm a giant nerd, in case you couldn't tell, but it's good that you find your calling as a nerd, right? And this is my use here. So this particular model comparison is done for you in Stata and in SAS, not in SPSS, which is this null model likelihood ratio test. What it did was take the minus 2 log likelihood from your current model that has 2 piles of variance, 5, 4, 4, and compare it to a model that has only 1 pile of variance, which was before here, which was a long way away, 602. So 602 minus 544 gives us 57. 57 is bigger than 3.84, so yes. That gives us an empirical basis by which to say, I like this one better. That's significant. A 2-pile model fits better than a 1-pile model, therefore its results should be more trustworthy. Now in my book, when I refer to these model comparisons, I always write minus 2 delta for change, log likelihood, and in parentheses give the degrees of freedom, and I have a squiggle in front of it, tilde. That's because some people will yell at you for taking the straight degrees of freedom and using the chi-square. There's like 20 people in the world who know and care about this difference. I am not one of them. But in case one of them is reviewer 3, I want you to know that technically speaking, you can't take straight degrees of freedom here. What is the smallest number that a variance should be? Not a trick. 0. Yeah. So to mimic the idea that your sampling distribution can't have a negative part to it, people would suggest that you should use a mixture chi-square distribution, where this test, rather than having 1 degree of freedom, is actually like a half a degree of freedom. It's a mixture of chi-square with degrees of freedom 0, which is a constant of 0, and half of it should be 1. So they would say, no, 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 the critical value is 2.71, not 3.84. And I would say, okay, fine, but mine's 57. So if you fall in that gray area between 2.7 and 3.8, you need to pay attention to this. But using straight degrees of freedom and regular chi-squares rather than mixtures will be overly conservative. So if your test is significant with the conservative version, you're good, and those 20 people cannot yell at you. By the way, the 2 degrees of freedom, such as if you're adding a random slope and a covariance with an intercept, instead of 5.99, it's 5.14. So the differences get smaller and smaller. So there's a literature on this. I want you to be aware of it. It's one of those things I just can't bring myself to care about too deeply. Sometimes models are phrased as whether we're adding things, and sometimes they're phrased as whether we're taking things away. So think of it this way. If you add parameters you're adding more stuff to your model, such as more piles of variance, your model can get better or not better. Better means it's significant. So what we just did is an example of going from a 1 pile to a 2 pile. We would want to know if we made the model better or not better. Removing parameters then is the idea of, is my model overly complicated? Can I get by with something simpler? In that case, you're asking if your restricted model is worse or not worse. That is what the chi-square test in SEM is about. The chi-square test that shows up on your SEM output is a -2 log likelihood difference between the saturated model, which is all possible variances and covariances, and the factor model that you said it had to do. So you're looking for not worse in that situation. So they come in these different kinds. It's a way of framing it, but it's useful for thinking about what you're trying to do. If you're trying to add something, the worst that can happen is that it's not better. If you're taking something away, the worst that can happen is not worse. There. Got it. I think I need more coffee. I'm starting to stutter. Okay. So we'll get more practice with that later this afternoon. Any questions on this idea here? 2 piles versus 1 pile? It's an empirical question how many piles you need, but your design should dictate whether or not you think to ask that question. Longitudinal data, 2 piles at a minimum, possibly more. When this can go wrong is when you have 3 or more occasions. This random intercept model says that the only source of correlation for occasions from the same person is the random intercept, and that's it. So people are only allowed to differ from each other in one way. But if people differ from each other in change, that can't be right. So, question? Yep. In longitudinal data, very, very, very rarely. In clustered data, perhaps. So if you really have groups where the people are either randomly assigned to them or like very nearly so, where group really doesn't matter, there would be a case in which adding that random intercept doesn't help. It would create a conditional interclass correlation of 0, and so it wouldn't change your inferences any. So it could happen. I don't think I've ever seen it happen in longitudinal data, though. No. I would ask for it as reviewer 3 if somebody tried to sneak in a clustered data sample and fit a regression to it. I'd say, well, you need to show me that the regression model fits just as well as the multi-level model then, before I'll believe you. That's what I would say. Does that help?
Yeah, it does. I never would have thought about that, but you say apparently it's reviewer 3.
I'm sorry? Yep. All right. So I'll be done with this example then, and then just say a few more words about the intersection of ANOVA and multi-level models then, and then we'll be ready for lunch. So picking up on slide 32, kinds of ANOVAs. So in thinking about classical approaches to data analysis using some kind of analysis of variance, there's 3 kinds. What I've just shown you is the contrast between what I would call between groups or between persons and adding a within-person component to get us to this univariate repeated measures ANOVA. There's another one that we'll talk about in just a second. For practical data analysis problems, ANOVAs can be limited. So if you have 2 occasion data and all your data is complete and everybody showed up at the exact time they were supposed to be measured, you want to do ANOVA? Fine. There's nothing wrong with that. There's absolutely nothing wrong with ANOVA when it fits the data. But more often than not, in longitudinal data, things get a little messy. And the restrictions of ANOVA are no longer appropriate. So the big one then, all kinds of what people call ANOVA, they mean least squares most of the time. And the problem with least squares is listwise deletion of whole persons. So the dropping of people who are missing occasions is a consequence of least squares. It's not a consequence of ANOVA. I can fit an ANOVA using proc mixed and not drop whole persons because it uses the stacked data structure where it uses all of the occasions that are complete. ANOVAs that are repeated measures do not allow time-varying predictors. Whatever continuous covariates that you have are between person variables only, level 2 only. So if you have a time-varying predictor, that's another reason to set up your ANOVA model as a multi-level model instead, even though functionally you can still think of it as an ANOVA. Time in ANOVA is balanced. ANOVA fits what is called a saturated means model, meaning that it estimates as many parameters as you have occasions. So what you would get as a main effective time, for instance, if you have 4 occasions, would take 3 degrees of freedom to create all possible mean differences. That requires you thinking about time in this discrete and balanced way. There's no room here for time 2.5 or time 3.5. All of these 3 kinds of ANOVAs have these same limitations. The way that they differ from each other is in their model for the variance and what they say about dependency of occasions from the same person. That's how they differ. So the straw man case that I would never fit for longitudinal data is the E-only single pile model between groups ANOVA. It says there's no dependency, no correlation of occasions from the same person, so it fits a structure that looks like this. So this is what's known as variance components or identity. Equal variance across my 4 occasions, no covariance whatsoever. The one that we just looked at takes dependency into account by making another pile of variance. It differentiates total variance into what is between persons in the mean due to the random intercept from what is within persons around the means due to the residual. So it says the total variance then is some part E and some part U0, but that is the same all the way across time. Equal variance across all occasions. It also says, and this is more problematic for occasions more than 2 types of studies, is that the only reason that occasions from the same person are related, the only source of this covariance here, is the random intercept. So the data are independent once you control for mean differences. It also says, if you think about it this way, time 1 and 2 are just as related as time 1 and 4. And people are just as different from each other at baseline as they are at the end of the study. And as my best of my PowerPoint drawing ability shows down here, that can't be true. If people change differently, they have to spread out. So this idea that you need different variance across time and different covariance across time then, that's where this model breaks down. So for more data that have more than 2 occasions, it's an empirical question whether this specification of compound symmetry, equal variance, equal covariance, is sufficient. The classical ANOVA least squares approaches talk about this as a violation of sphericity, which actually is a little less restrictive than compound symmetry. It means equal differences, equal variance and covariance of the differences between occasions. And then if that is wrong on your output, you're given like 4 different versions, like Wind, Felt, and Greenhouse, Geyser, and all these people who like wrote their dissertations or something, making up new versions of F statistics. That's like putting a Band-Aid on a broken arm. It makes the whole thing more conservative, but it doesn't solve the problem as to why compound symmetry doesn't fit. It doesn't allow you to add anything to the model that makes it more realistic. So in the open in case of emergency version of ANOVA then is the multivariate approach. So this is what's known as MANOVA, multivariate analysis of variance, where rather than trying to approximate the variance and covariance with just a random intercept variance and just a residual variance, you're like, screw it, just let everything be what it wants. That's the multivariate approach. So there are as many variances as there are occasions, and there are as many separate covariances as there are pairs of occasions. So for instance, for 4 occasions, a multivariate model for the variance here would take 10 parameters. Here's the formula for how many parameters it takes. SEM folks will recognize this. So if I had, say, 100 occasions, how many parameters would this take? A lot. 100 times 101 divided by 2. And we haven't even talked predictors yet. So at a minimum, you need as many people as parameters to estimate this thing. So it is possible to do this in small occasion data sets, 2 or 3 occasions, lots of people. This is fine. It starts to fall apart for 2 different reasons. One is lots of occasions relative to few people, and the other is this idea of balance. The whole sample has to share this structure. There's no row for time 1.5, time 3.2, time 4.1. This assumes discrete time. So if you have unbalanced data, you can't do this. So ANOVA is like those t-shirts that say one size fits most. Like, no, actually it doesn't. So it gives you 2 choices. Either everything is the same across time, or everything is different. What we're going to do is find a way to let things be different, but different in a pattern. Different in patterns that can hopefully do as good a job as letting everything be different, but take fewer parameters, be interpretable with respect to the parameters, and also allow for unbalanced data. So that's really the hallmark of MLM here. It's flexibility. Besides saturated means, we can treat time as continuous and estimate trajectories through the means that have shapes. We can think about linear versus nonlinear change or piecewise change. On the variance side, then, we can allow random versions of each of those terms. People can get their own linear slopes or their own nonlinear slopes. That, in turn, changes this pattern into something that looks more like let everything be what it wants than the previous ANOVA, but hopefully is simpler to do and doesn't require complete data. So there's nothing wrong with ANOVA when it fits the data. This multivariate ANOVA will always fit the data best. This is the answer key. This is what's known as the saturated model in SEM, the H1, as it were. So relative to this is the answer key. We can do likelihood ratio tests for -2 log likelihood differences, where everything is going to be some shade of worse or not worse. But we can only get this answer key for balanced data. And so that's why, for those of you who are thinking about this type of growth modeling in an SEM framework, if you have balanced data, it is possible to do absolute assessment of model fit. You get CFI and TLI and RMSEA and SR, MR, and all those letters that tell you if your model fits in an absolute sense, because it has this answer key to come back to as to what the rightest answer is. But if you invoke T-scores and M+, which says, well, the data are unbalanced, there's no more answer key, there's no more fit. Absolute fit is only possible if you have balanced data. If you have unbalanced data, you don't know what the right answer is. Then all you're left with is relative fit, which is this idea of -2 log likelihood of one model versus another. You can always say this is better or worse than some alternative, but you don't have a sense of how good it is in an absolute sense. So absolute fit is based on this model for the variance. It's only possible for balanced data. And this model is only possible to estimate if your data are complete when using least squares. It is possible to estimate it if your data are incomplete but balanced using some kind of maximum likelihood. There. Questions? All right. on schedule. Wow. That so rarely happens. That's exciting. So we have a lunch break then until, let's say, 1:15. Does that sound good for folks? We'll meet back here, and I am told that there will be someone in the room, so you can leave your stuff if you wish. And I will see you then.